Our next speaker is Gordon Osinski, and his talk is on field investigations of impact terrains with modern tools. Are you online, Oz?
I am here. Can you hear me okay?
I can read you loud and clear. Go ahead.
Excellent. Okay, well, tough act to follow. I think the second time in my career I've got to follow Jack and talk about something a little different. Yeah, it's a pleasure to be here. Thank you to the speakers for this opportunity. So let's jump straight into the next slide, please. So first, a quick pretext. I'm sure most people on the call know why we're studying and why we're going to talk about impacts today. Really two major geological processes that are affecting the surface of the moon and have done in the past, and it's volcanism and impacts. So quite different to the Earth, where impacts are few and far between, although I'll get to that in a second. I'll make this point a couple of times, but impacts are complex. Some parts of the moon and where we're going to first are literally saturated in impacts, crater upon crater, and a lot of the material on the surface, or most of it, will be not in situ. On the bottom right, one of the biggest specimens in the Apollo sample lab, the products of meteorite impacts are also complex, heterogeneous, and change on a centimeter, decimeter, meter scale. Next slide, please. So I'm going to talk today and give you a perspective from looking at meteorite impact craters on Earth. I must say this was a challenging presentation to put together, having worked on craters now for 23 years on Earth into 15 minutes. Quickly, if you are interested in the terrestrial impact record, it does change year to year. Impactearth.com. You can go to there and check out, details about all the craters we know about on Earth. And I did want to make this point after both Jack and Dean's talks, because this is important for training. It's really quite interesting. At Apollo, we only had 12 confirmed meteorite impacts on Earth, none of them very large, and about 30 or 40 suspected impacts, of which, interestingly, Sudbury was actually only suspected at that time. We now have 201 confirmed impacts, and so in terms of our knowledge base and places to go and train the Artemis astronauts, we have a huge new variety of craters that I hope we keep in mind. So not just repeat where we went to during Apollo. Next slide, please. Of course, I'm coming to you from Canada, and there's a great, fairly local, not too far away, impact record here in Canada. 31 confirmed impacts, some fairly fresh, well-exposed craters, ranging from, our own meteor crater up in the top left, to all the way up to Sudbury. Next slide, please. So again, I'll come back to this a few times. Impact craters are complex, and this is one outcrop from the Mestastin Lake impact structure that's about 4 or 5 meters high, and the lithologies, the impact lithologies, are changing, quite drastically over a very small area. And so I'll come back to this again in the future about context. Next slide, please. I always like showing this slide when doing this kind of presentation about field geology. Some of my colleagues' offices in the Department of Earth Sciences here at Western don't look too dissimilar for this, which is from one of Scott's expeditions in 1911. We're still using pen and paper quite a bit in geology. We're slow to catch up, and again, that's something I'll re-emphasize later on. Next slide, please. We have been hearing this, that I would actually consider as right in the middle of a revolution in field geology, with a huge number of new techniques that we can apply in the field. To pick up on one of Dean's points, though, a lot of these are they optimal? A lot of these take a lot of field time away. And so, I do think there's some unanswered questions that hopefully we'll get to in this workshop about, when and where, or even if certain techniques will be used. I don't have probably time to talk about it too much today, but I hope it's a topic we can cover at some point too, is, this lab in a hab doing analyses in an evening is something that we've been doing quite a bit, in particular with the geochemical analyses. Next slide, please. So, not able to talk about all of these techniques. You can just click through these, I think, Ryan. I noticed they're kind of back to front. But again, over one outcrop, and there's a couple of people in there for scale, we have a change in lithologies from essentially, impact breccias with a little bit of melt to pure impact melt rock over about 2 meters. So context is really critical. And if we don't know where the samples we collect on the moon come from, to within a centimeter or so, I'd argue that we're not going to get our bang for the buck. So with that in mind, I'm just going to focus on, a few techniques that we've been applying over the last few years. So next slide, please. So I think a key part of this is standoff imagery. This is perhaps a little extreme. You're looking at a hill of columnar jointed impact melt rock at the Mastastine impact structure from, a kilometer and a bit away. But the idea of having some imagery of the outcrop with the astronauts in view, I think is very key. It's something that has really enabled us to do a lot more with the data we have. You can only see and understand a certain amount when you've got your face up at an outcrop. You cannot walk back too far. So we've been experimenting, starting probably a decade ago with this is a gigapan setup on the right hand side. Essentially digital elevation camera, sorry, not digital elevation, digital SLR, stitch together a number of high resolution images and you get a great panorama. Of course, that's only a 2D image. So next slide, please. So I've been applying LiDAR for quite a number of years now. And, the beauty of LiDAR is that you get this three-dimensional view and, quantifiable information about size and everything too. So this is the same image of that outcrop there. This is this famous Discovery Hill outcrop at the Mastastine Lake impact structure. And hopefully if you can zoom in enough, you can see nice columnar joints in this outcrop. Next slide, please. So LiDAR, when I first kind of read about it in the context of the Canadian space program anyway, was being talked a lot about for rover guidance and navigation, hazard avoidance, how to get from A to B without running into things, tripping over things. But I think, as people have realized over the last decade, LiDAR, I actually think is a valuable scientific tool as well. And I actually think even more valuable as a scientific tool on the moon than it is here on Earth. The reason for that is a good example on the screen here. So this is from the Horton impact crater, Devon Island in the Canadian High Arctic, 24-hour daylight. And you'll see, this is actually taken quite late in an evening. Excuse me. So, sun's at quite a low angle and a lot of that outcrop is in shadow. And I hope you'll agree that top image is not particularly useful in terms of, both recording what we're seeing and demonstrating what we're seeing. But then the bottom image, what we're looking at is, not just XYZ data from LiDAR, but the intensity data. So this is not particularly relevant to the moon, but the high intensity areas are actually equator zones with increased hydrothermal alteration. But the point being is that you can use LiDAR to actually get some information about the geology of the outcrop. You can see layers and potential faults in that outcrop that you just cannot see even without, I would argue, the best visible image, even if it wasn't in shadow. And so, with illumination conditions at the pole, one of the most valuable tools I've been using in recent years in the Arctic for some of the same reasons, I think, as LiDAR. And I hope a bit of a pitch for LiDAR there for the moon. Next slide, please. Of course, another way to get standoff data, we're seeing this in action on Mars. Not going to work the same way on the moon, but potentially there are other different types of technology that we can use, which is drones. And so this is definitely, for the field geologists out there, drones are opening up just a huge number of different areas, providing different data sets that we never had. I started off with, the off-the-shelf wee little drones. This is now, a 25, 30K DJI Matrice drone, much more capable, can fly LiDAR, different types of sensors. And it gives you the type of image I'll show on the next slide, please, which is again going up to the Mistaston Lake impact structure. So, when I first went to Mistaston, there was a grainy black and white image in one of Richard Greaves' papers to go off for Discovery Hill. But with drone-based data, we now have this. And if you zoom in again, next slide, please. We're just gonna, this is collected last fall, and we're just beginning to scrape the surface on what this is showing us, right? I forget, yeah, my cursor won't show up here. In the middle of the screen, there's actually a person, and if you look on the left of the outcrop, there's a red climbing rope, and I'm dangling partway off it. So this is about 60-meter high vertical cliff, and then it goes further down. But you can get, this information in here that we haven't published on and nobody has in terms of, cooling. You can see breaks in the columnar jointing as you come down that outcrop. And so again, the value of standoff data, I think, is really quite critical. Next slide, please. Data fusion, so bringing together even more techniques. It's challenging to do in real time. You can do this with a lot of post-processing, but I do want to kind of demonstrate the value. So this is now going to the Reese crater in Germany. What you're looking at in the top left is a combination of a drone-based 3D model with LiDAR, which is shown in the bottom right. I don't know if Mike Zanetti is on this call today, but that's Mike down in the bottom right. So we've got, a LiDAR-derived RGB composite image in the top left, and then we collected both in real time and after the field LIBS data that I'm not going to go into today, so compositional laser-induced breakdown spectroscopy data. But what it is or was used in the bottom left image was UV visible near-infrared spectroscopy. And I visited this particular quarry at the Reese many times. You can see a 5-meter scale there. Collected many samples, but we're just not able to, see. Well, we haven't seen the geological complexity in this outcrop before until we kind of did this. So what you're actually looking at, the upper unit is this so-called swavite, the melt-bearing ejector. The bottom, where you see the blues, the greens, the reds, and the yellows, is this ballistic ejector. And, we're seeing a lot of compositional complexity that we didn't know existed before. Next slide, please. So I did want to, come to this too, because, this geological revolution we're in, where we have, potentially an endless number of different types of data sets, different types of technologies that we could take to the surface of the moon too. It brings with it additional challenges that we should not forget. We've got to get all of this data off, typically very different devices. We've got to co-register, correlate, and still, today I think many, probably the majority of geologists still have, that good old paper field notebook, and we've still got to digitize data as well. So with this in mind, the final kind of couple of slides, not seeing something that existed out there. So this is being designed for, terrestrial field geology, but I do think aspects of this could play well into, field work under the planetary bodies. So this is currently an iOS-based app, but we're moving into Android, and this is essentially what we're trying to do here is to bring all of these 8 different things together into one app that you can run on a tablet. So, you can take photographs, you've got GPS-enabled tablets, you've got your notes and sketches, you can record audio, etc., etc. Running out of time, so in the last minute, just go to the next slide, please. We're keeping some of the key things that we think are important. So, when it comes to sampling, it doesn't show up too well here, but you can, when you collect a sample, you can choose on a bunch of images that you've taken exactly, to the nearest millimeter or centimeter where that sample came from. Next slide, please. One of the other key thing is being able to draw sketches. So, typically you would draw a separate sketch to your field photograph, but you can do that all together in this one application. And I believe that is, yeah, maybe one other wrap-up slide. This is in development. This is actually Josh Kutchik, Matt Dominic, a couple of astronauts testing out this app at Mr. Aston just last fall. If you're interested in learning more, happy to share a prototype with you and get some feedback. And that is it. Thanks, Jose.
Excellent. Thanks, Oz. That was great.